Hello and welcome to Learning JavaScript Data Structures and Algorithms. This course is about data structures and algorithms in JavaScript. The course will utilize real-world data sets, how data structures and algorithms can be used to solve programming problems. My name is Rodrigo Silveira, and I will be your instructor throughout the course. By means of introduction, I've been using JavaScript professionally for the better part of the last 10 years. I currently work for a software company based off of Utah, where we have several teams working on very large code bases, building JavaScript, PHP, and Android applications. As for my formal education, I hold a bachelor's degree in computer science from Brigham Young University, Idaho. Recently, I have published 2 books with Peck Publishing on the subject of game development in HTML5 and JavaScript. The first half of the course will focus on teaching you the most widely used data structures. These are arrays, linked lists, sets, queues, stacks, trees, and graphs. The second half of the course will go over algorithms and complexity. We will talk about how to measure complexity using big O notation. Finally, we'll go over several sorting and searching algorithms. By the end of this course, you will be familiar with data structures and how to use them in JavaScript. You will also learn how to analyze, write, and use algorithms in order to build highly efficient applications. Before proceeding with the rest of the sections, be sure that you're familiar with the basics of JavaScript programming. If needed, take some time to freshen up on topics such as JavaScript prototypal inheritance, closures, and JavaScript's asynchronous paradigm. Welcome back to Learning JavaScript Data Structures and Algorithms. We're in the first section. In this section, we'll talk about data structures and algorithms, what they are, and how we can use these concepts to keep the challenges involved in writing complex systems under control. In this video, we're going to take a look at the challenges involved in building large and complex applications in any language. We will then look at a fundamental way to manage the complexity found in large systems. Writing software of any significant size is no trivial task. As the complexity of the software goes up, the amount of time and effort that it takes to understand, maintain, and extend and debug the software also goes up. While there are many techniques to help you assess, calculate, and manage this complexity, this course will focus on the most basic and fundamentals of all of these techniques. Our focus will be on using well-known data structures and algorithms to help keep the code base organized, easier to understand, and less intimidating to maintain. A software data structure, as the words imply, is a way to organize data efficiently. An array, such as the one natively found in JavaScript, is a very good example of a data structure. An algorithm, on the other hand, is a self-contained set of operations that produce some output. For example, sorting an array of objects in a particular way. Since JavaScript is a very loosely typed language and has a low barrier to entry, it's not difficult to quickly pile up hundreds of unrelated lines of code relying on object literals to express your data. As you likely have experienced firsthand, working on such a code base is not where you want to spend much of your time. By using well-studied data structures and algorithms, your code base becomes easier to read by you and by other engineers. It also makes it easier to apply design patterns and other techniques that will help you keep control of the complexity of your application. In summary, complex applications are difficult to build and take significant effort to maintain. Using common data structures and algorithms help to give order to your code, thus making the development lifecycle more manageable. In the next video, we'll take a look at why you'd want to use data structures and algorithms in JavaScript. In the last video, we saw some reasons why developing large applications is so difficult. We also saw how we can leverage data structures and algorithms to manage complexity. By encapsulating the problem domain into relevant data structures, we can think of the various components in a system at a higher level of abstraction. This is the third video of Section 1 on JavaScript data structures and algorithms. By the end of this video, you will know why data structures and algorithms are so useful in building large JavaScript applications. In this video, we're going to take a look at some reasons you'd want to use data structures and algorithms in JavaScript. We will then go over all the data structures and algorithms that we'll be using throughout this course. As mentioned in the previous video, without proper data structures, large code bases can be difficult to build accurately and to maintain. In the world of JavaScript, this is becoming particularly meaningful as the size and complexity of applications grow. Not only are we seeing more and more JavaScript applications deployed to browsers, but there are now many large applications built on top of Node.js, which is a JavaScript runtime built on top of Chrome's V8 JavaScript engine. We'll begin this course by going over more traditional data structures such as arrays, linked lists, and sets. We'll also talk about other widely used and very powerful structures like queues and stacks. Finally, we'll take a look at more advanced and complex data structures such as trees and graphs. Next, we'll focus our attention on algorithms. After going over big O notation, we will look at various searching and sorting algorithms, namely depth first and breadth first search, bubble sort, merge sort, and quick sort, linear search, and finally binary search. In summary, modern JavaScript engines make complex applications possible. Using data structures is an important strategy to getting us there. In the next video, we'll explain how each video will be presented and how we'll exercise our newly gained knowledge with a hands-on real-world example. In the previous video, we discussed some of the reasons why data structures and algorithms are such an important subject in JavaScript development. This is the fourth video of section 1 on JavaScript data structures and algorithms. This will be a short video where we'll go over the format of the subsequent videos. In this video, we'll get acquainted with the format of the various examples that we'll use in future sections. At the beginning of each video, we'll explain the data structure or algorithm being discussed. We'll go over what it is, what it does, what problems it solves, and when it would be appropriate to use said structure or algorithm. Next, we'll go over a simple implementation in pure JavaScript. Then finally, we'll go over a specific example of how to use the data structure or algorithm described in that section. The examples will use data representing a fictitious news provider website. So look at the examples in this context, such that the data models things such as articles, authors, comments, etc. This fictitious website will model data representing the various news articles found on the site, which can be composed of the following: an author, title field, a published date, a list of tags and categories, one or more media assets, comments, etc. We can further break down the parts of the article data model into their own components, such as an author object, modeling a first and last name, as well as a URL to a photo representing the author. Media data models can be constructed having a type, either an image, a video, or an audio asset, the size of the file, the duration of the asset in the case of a video or an audio file, and the URL to the actual file. We can also have comment objects composed of an author, a timestamp representing when the comment was published, and the actual body of the comment. In this section, we learned how we can build large applications in a predictable and maintainable way through the use of data structures and algorithms. We also saw why this is particularly important in JavaScript applications. In the next section, we'll get started with the first three data structures in the course: arrays, linked lists, and sets. In the last section, we introduce you to data structures and algorithms and why this is such an important subject to JavaScript development. This is section 2, arrays, linked lists, and sets. In this section, we'll get our feet wet by looking at three data structures to get us started. The first structure we'll look at is the array, which you're probably already familiar with since JavaScript provides a native implementation of arrays. Next, we'll talk about linked lists, which for some reason aren't as popular in dynamic languages as arrays are, but are still just as powerful a construct. Then finally, we'll talk about set, which although they're pretty straightforward, we can solve some pretty complex programming problems using them. In this first video, we'll talk about arrays. After describing what arrays can be used for, we'll look at the most commonly used operations in arrays in JavaScript. Then we'll take a look at the transformation operations added to the arrays prototype in ECMAScript 5. And finally, we'll take a look at a hands-on exercise to help you put arrays to good use. Anyone who's been programming for longer than a day are likely already familiar with what arrays are. In any case, an array is a container of elements that allows us to group related data together. In most programming languages, arrays are implemented in such a way where every element in the array lays in memory next to one another. This means that we can very efficiently access any arbitrary element within the array by simply performing arithmetic on the memory address of the array. In JavaScript, things are a little different. And the reason is that arrays are really implemented as objects, where the keys are numerical values representing the index offsets of the various elements. What this means is that there is no relationship to where an element is within the array and where that element is actually stored in memory. But other than this slight detail, arrays are still arrays in JavaScript, and we can accomplish some pretty powerful things using them. To create an array in JavaScript, we can either instantiate the array class, or we can use the array literal syntax. The most commonly used operations in arrays are probably push, pop, and index of. The most common way to put an additional item inside an existing array is by sending the new element to the push function. This will append the new element to the end of the existing array. In contrast, we can remove an element from an existing array by using the pop function, which removes the last element from an array before returning it. If we pop an empty array, the return value is undefined, since there's no elements defined in an array that has no elements. Finally, we can search through an array by using the indexOf function, which takes an object for its input and returns the index of the first element to strictly match against the input. If no matches are found, the return value is -1. There were several new functions added to the prototype of the array class in ECMAScript 5. Most of these functions allow us to iterate through the array, applying a callback function to every element of the array. The output of these functions is usually a new array, leaving the original one unchanged. Two common such methods are map and reduce. Array.map takes a callback function which takes as its argument each element of the original array in turn. All values returned from array.map are elements in the new array created by the function. The original array remains unchanged. Array.reduce also takes a callback function, but it returns a single value instead of a new array. The arguments to the callback is an accumulator object, and each element of the original array in turn. For a demonstration of how we could use arrays in our fictitious news website, imagine we have an array with objects representing authors that post in the website. The user wishes to see the names of all the authors who have posted in sports. We could accomplish this by creating an empty array, iterating over the list of authors, finding authors that posted in sports, and then pushing the name of the author to the previously defined array. Alternatively, we could use array.filter to create a new array that only contains author objects if the author has posted in sports. We could then map over this new array and only return the name of the authors in the filtered array. The output will be exactly the same in both cases. In the next video, we'll take a look at linked lists, which are similar to arrays, but offer some pretty interesting trade-offs. In the last video, we went over JavaScript arrays, and a few of the transformation functions added to the array prototype in ECMAScript 5. In this video, we will focus on linked lists. We'll first compare and contrast linked lists and arrays at a conceptual level. Then we'll talk about specific implementations involved in JavaScript's implementation of native arrays. We'll begin by looking at what linked lists are and how it differs from and complements an array. Next, we'll take a look at the supported operations of a linked list. We will then implement a simple linked list class in JavaScript. Finally, we'll work through a simple use case. We're going to use a linked list to manage a list of new articles on our fictitious news website. As a quick recap on arrays, its main feature is that every element is laid out in memory side by side, such that we can access any element in the array simply by performing arithmetic on the base memory address of the first element of the array. In other words, while the main benefit offered by arrays is the constant access time, one of the most obvious drawbacks is that an array needs to be laid out in a single continuous block of memory. If the array we need to allocate is larger than the memory that we have available, this could obviously become a problem. Like an array, a linked list is a linear collection of elements. Linked lists are made up of a collection of individual nodes. A node has a data attribute where we store the actual data related to the being represented by the list, and it also has a next attribute that points to the next node in the list. The last node of a linked list will always have its next attribute pointed at null, thus indicating that there are no more nodes in the list. Unlike arrays, linked lists are not laid out in memory sequentially. Since each node is created separately, the actual location of each node in memory is irrelevant, but is also not controlled by the application. One downside to this is that we cannot predictably calculate the memory location of an arbitrary node in the list relative to other nodes, meaning that we need to traverse the entire list from beginning to end just to access a specific node within the list. This means that the speed it takes to access a particular node in the list is directly proportional to the length of the list. The longer the list, the longer it will take to find the node we want. One of the benefits of using linked lists is that we don't need to know the total size of the list up front, and thus we don't need to allocate very much memory at all when first creating a linked list. All we need to do is create a single node, which is a pretty small data structure. Then, whenever we need to add to the list, we simply create one additional node and connect it to the next attribute of the previous node. Growing a linked list one node at a time makes them efficient, both in the sense that we never take up more memory for a linked list than we need to, as well as in the sense that we don't need to have a very large block of continuous memory available when using large lists. Another major benefit of linked lists is that adding and removing elements to the middle of the list is very fast. If we wanted to add an element to the middle of an array, we would need to either shift every element of the array after the insertion point or create an entire copy of the array in memory. Either way, the operation would be inefficient, either in terms of memory usage or the number of operations involved. In contrast, adding an element to the middle of a linked list is quite trivial, since all we need to do is create a new node, then change a couple of next attributes around. The operation is efficient both in terms of memory usage and computation cycles. As a side note, given the way JavaScript implements its native arrays as objects, the actual low-level implementation of arrays may be different than what we have just discussed. However, JavaScript 6 introduced the typed array data type, which is a special type of arrays compared to JavaScript's native arrays, which allows us to create actual array structures as we described earlier, giving us all the benefits of using real arrays. The four most common operations in a linked list are add, delete, clear, and has. To add elements to an existing linked list, we can use the add function, which, similar to an array.push, it will add the incoming data to the end of the list. Additionally, we could add an element to any place in the linked list simply by providing a reference node, which will make the new data be added to the left of where the reference node was. Similarly, we can remove an element from the list by using the delete function, which behaves much like array.pop. This removes the last element from the list and reduces the length by 1. We could also provide a reference node which removes the node itself regardless of where it is in the list. Finally, instead of deleting one node at a time, we can also delete every node from the list by calling the clear function, which removes all of the nodes and resets the length back to 0. If we want to determine whether a node is in the list or not, we can use the has function. This function works similar to array.indexOf, but instead of returning the actual node or its position in the list, it simply returns true or false. The actual location of a node in the linked list is irrelevant in most cases. We can iterate over a linked list, first by getting a reference to the first node in the list, which we can do by referencing the head attribute of the list. Once we have a reference to the first node, we can simply get the next node by accessing the next property of the node. Doing this, we can iterate over the entire list by continually accessing the next node in the list. When the next attribute points to the null object, we know we have reached the end of the list. We will now look at a simple implementation of a linked list class in JavaScript. The first thing we need is a node class. Here, this class will expose two properties, the next pointer and the data attribute. Next, we need the linked list class itself. This class will define a reference to the head and tail nodes, as well as an auto-updating length property that represents the current length of the list. The add method takes a data object and creates a new node from it. The new node is then added to the end of the list, similar to an array.push. By default, the delete method removes the last node from the list. However, if the optional node parameter is passed to the function, we will first attempt to find the node in the list and stitch the next pointer to its parent to the node's own next. Doing so allows us to remove any node from the list. The clear method simply resets the length property of the list back to 0 and clears out the head and tail properties. This way, the garbage collector is able to get rid of all of the nodes that were being held by the list. Finally, the has method iterates over the list and returns true as soon as it finds a matching node to the one provided. Optionally, we could have done similar to the array functions and accepted an anonymous callback function that allows the user to specify if a match was found in the list or not. Now let's take a look at a real-world example of how to use linked lists in our fictitious news website. The use case for this demonstration is that we have a list of article objects representing articles in the website. Every article object will have an ID, a title, author, published date, and the actual body of the article. What the user wants to do is to be able to effectively add new article objects to this list, making sure that the new article is added to this list just before the last article currently in the list that was written by the same author. To accomplish this, we will first take this array of articles and convert it to a linked list. Once we have the articles stored in a linked list, we can add the new article to the right position simply by iterating over the list, beginning at the head and looking for the first node in the list that was published by the same author as the one in the article we're trying to insert. Once we have this node, we can simply send it as the reference node to the add function as we described earlier. In this video, we talked about and implemented a linked list class. In the next video, we'll take a look at how sets compare and contrast with arrays and linked lists. We'll then take a look at ECMAScript 6 native set class along with its accompanying API. In the last video, we took a look at linked lists and implemented our own abstraction for them. In this video, we'll talk about sets. Thankfully, ECMAScript 6 already implements a set class, so we won't need to implement our own abstraction for them. To begin, we'll define what a set is, looking at it from a mathematical standpoint. Next, we'll go over the supported operations in the set object. We will then wrap up the section by going over a real-world example of using sets to associate tags to an article in our fictitious news website. So what is a set? If you squint hard enough, you can actually see an array in a set. Formally speaking, a set is a collection of unique objects. Objects stored in a set can be simple, native types, complex objects, or they can also be sets, so that we can have sets of sets. The current ECMAScript 2015 spec describes 6 operations and 1 size property in the set. Although the name is different, the size property in the set behaves exactly the same as the length property found in the array. The 6 properties we'll look at are add, delete, clear, has, values, and for each. To create a set, we simply need to instantiate the set class constructor. Unfortunately, as of this recording, there is no such thing as a set literal notation, similar to how we have array literal and object literal syntax for convenience. The add function takes a value or a reference to an object and adds it to the set. The way JavaScript determines if the incoming object or value is unique is by performing a strict comparison. In other words, if the incoming value is a native type, the comparison behaves the same as double equal or triple equal. However, if an object is sent, the reference of the incoming object and every object in the set must match in order for the objects to be considered non-unique. The delete function must always receive a reference to the actual object that we wish to delete. The return value will be true if the object was successfully removed from the set and true if the object was removed. In this case, although this object being added and this object being deleted have the same values, they each represent a different reference to these objects in memory, and that is the reason this call to delete returns false. Remember, to delete the object, we must send the actual reference to an object in the list that we wish to delete. To delete every element from the set, we can call set.clear, which, as you would expect, removes every element from the set and sets the length back to 0. Similar to our implementation of linkedList.hash that we implemented in the last video, we can search through a set and determine if an element is found inside the set. The key to remember is that strict comparison is used in order to determine whether an element contains inside the set. The return value will be true if the element is found and false otherwise. The values function returns an iterator object holding each element in the set sorted by insertion order. With the iterator object, we could manually iterate the set by pulling the iterator's next object until its done flag is set. Alternatively, we can leverage ECMAScript 6 iterators and use the for-of loop to help us iterate the set with much less code. Another way of iterating over the set is to use the for each function defined in the set's prototype. This works exactly the same as the for each function defined for arrays. The supplied lambda is applied on each object, on each element in the set, receiving the object and the set itself as arguments. Getting access to the set can be helpful when we need to modify the set mid-iteration. For this video's practical example of how to use sets on our website, let's assume that every article in the website is associated with 0 or more tags provided by the user. Since the user is providing the data to us, we don't want multiple copies of the same tags to be found throughout the system. So one way to assure that all of the tags are unique is to store all of the tags in a set. So by iterating over the list of tags provided by the user and storing them in a set, we can be sure that no duplications will be found in our system. In this section, we introduce you to 3 data structures, 2 of which are natively supported in modern JavaScript. These were arrays and sets. Since linked lists are not natively supported in JavaScript, we created our own and simple implementation of it. We also looked at different ways to iterate over these collections, including manually looping over the collection, using JavaScript's new iterator objects, as well as taking the more functional approach and using array transformation functions. In the next section, we'll learn about 2 additional structures, queues and stacks. Although both of these structures are linear containers, the way the data flows in and out of them is what makes them unique and so interesting. See you then! Welcome back to Data Structures and Algorithms in JavaScript. In the last section, we covered 3 types of collections: arrays, linked lists, and sets. This is the first video of section 3, where we'll talk about 2 special kinds of lists, queues and stacks. First, we'll cover queues, which are lists that enforce the first in, first out rule. Items that are inserted into the list first are used or removed from the list first. Next, we'll talk about stacks, which are lists that enforce the last in, first out rule. While the 2 rules that these structures are built on may seem simple, there are very powerful algorithms that are solved using queues and stacks. Let's get started by looking at queues. We'll start out by looking at what a queue is and what kinds of problems we can solve with them. Next, we'll go over the supported operations on a queue. After that, we'll look at a simple implementation of a queue class in JavaScript. Finally, we'll go over a real-world example of using a queue to perform background I/O tasks. Queues are lists that preserve the insertion order of elements, such that the first element added to the list is the first item to be removed. You can think of a queue much like the line at a supermarket, where you stand behind people waiting for your turn to process your purchases with the cashier. People exit the line in the same order that they entered it. The same idea is implemented in a queue data structure. A common use case for a queue is a task queue. Tasks to be performed are added to a queue, then they're processed in the same order that they were added to the queue. The usual operations in a queue are enqueue, dequeue, and length. The enqueue operation adds elements to the queue. Remember that elements are always added to the end or the back of the queue. The dequeue operation is the opposite of enqueue, which you can think of behaving similar to an array.pop. Items are always removed from the front of the queue. And length, which is not really an operation, is a simple property that lets us know how many items are in the queue. At the heart of our queue class that we'll implement in this section will be an array, which we'll use to store all of our items. For convenience, we'll allow the constructor to receive an existing array that we can wrap by our abstraction. In order to further hide implementation details, we'll expose our own length property. The enqueue function takes an item and pushes it to the end of the queue. Since we're manually keeping track of the length of the queue, we need to be sure and increment the current length property. Finally, in order to maintain a similar interface to the array, we return the same thing that is returned when you call array.push, which happens to be the new length of the array after the new item is inserted. Dequeuing an item is almost as easy as popping an item off of an array. The 2 differences are that first, we need to decrease the length property if prior to the dequeuing operation, there's at least one item in the list. Second, we remove and return that item that was currently sitting at the front of the queue. Thankfully, JavaScript provides a shift function on the array's prototype, which does just what we want. If the queue is already empty prior to the dequeue call, the output will be undefined and the length will remain 0. In this example, we'll use our queue inside a RESTful API that we can call from our application. Instead of making the client wait for the API to process and persist the data, we can schedule the associated task using a queue. Whenever some other script processing the tasks in the background calls a complementary API, the task is removed from the queue and the application is then free to do with the data whatever you want. In the next video, we'll take a look at stacks, which are similar to queues in the sense the data flows in and out of the stack in the same way, although stacks provide an interesting twist to them. In the last video, we talked about how to use a task queue to push I/O tasks to a backend processor, thus making the front-end API more responsive. Now we'll look at stacks and what sorts of things we can do with them. We'll begin this video by looking at what a stack is and what problems they solve. We'll look at the commonly supported operations in a stack data type. Next, we'll go over a simple stack implementation in JavaScript. Since one of the most useful use cases for a stack is in search algorithms, we'll look at the real-world hands-on example of how to use a stack later in the course when we get to section 5. Stacks are lists that preserve the insertion order of its element, such that the last element added to the list is the first one to be removed. To help you visualize how a stack works, think about a teacher grading a pile of homework assignments. The papers are stacked one on top of the other. When the teacher is ready to grade the papers, he or she will take the first paper that lays on top of the list, which was also the last paper added to the stack. That paper is then graded, and the teacher moves on to the next paper on the stack. Eventually, the teacher will get to the last paper on the list, which happens to be the first paper that was first added to the stack when the teacher first laid that paper on top of the table. Eventually, the stack will go away, and it will have a length of 0. A common use case for a stack is for keeping track of actions taken by the user, then making it possible to undo these actions. Every time an action is taken in the system, we can push that action into a stack. Should the user decide to undo one or more of these actions, we can simply take the last action that was pushed on the stack and call undo on that object, and the last action will be reversed. The interface for a stack is pretty similar to a queue in the sense that we simply add items to and remove items from the container. The difference is how the items are added and removed behind the scenes. The push function adds an element to the top of the stack, much like an enqueue would add an item to the end of a list. The pop function removes whatever item is currently sitting at the top of the stack, which is the complete opposite of how a queue's dequeue function works. Remember, queues are first in, first out structures, and stacks are last in, first out. Finally, the top operation only returns a reference to whatever is sitting currently at the top of the stack without actually altering the structure of the stack. The constructor of our stack class doesn't take any arguments. All it really does is wrap an empty array and hides away its implementation by keeping track of its own length. The push function simply increments the length and adds the incoming value to the end of the array. To be consistent with the queue class that we created in the last video, we return the new length of the stack after the push operation. The pop function works much like we would expect. It removes the item from the top of the stack, decrements the length, and returns the item that used to be at the top of the stack. If we only want to see what's at the top of the stack, but not actually change the stack structure, we can call the top function, which only returns a reference to the item on top of the stack. If the stack is empty when we call top, the return value will be undefined. In this section, we learned how to implement and use a queue and a stack. We will see how to use a stack to search through a maze later in the course when we talk about search algorithms. In the next section, we will conclude the data structures part of the course by learning about trees and graphs. Welcome back. In the last section, we covered queues and stacks. This is the first video of section 4, where we'll talk about the basics of graph theory by looking at trees and graphs. First, we'll cover trees. More specifically, we'll learn about binary trees, which are very specific and a powerful type of tree. Next, we'll talk about graphs and how they can be used to power a recommendation engine for our websites. Let's get started with trees and binary trees. We'll begin by looking at what a tree is and what kinds of problems we can solve using them. Next, we'll go over the supported operations of a tree. After that, we'll look at a simple implementation of a binary tree using JavaScript. Finally, we'll go over a real-world example of using binary trees for lightning-fast search. A tree is a data structure composed of a set of vertices or nodes connected by edges. Most commonly, a tree will have a special node called root, making a tree a hierarchical structure. A popular application of trees you'll certainly work with is an HTML document, where the HTML tag is the root of the tree and all other nodes are children of it. A binary tree is a special kind of directed tree that enforces the simple rule that no vertex has more than 2 children. Also, the order of each vertex is special in a binary tree. A left node's child has a lesser value than its parent, and the node to its right has a greater value. Because of these two features, we can find any node in a binary tree with very few steps, since at each step we reduced our search space in half. For example, if we have a sorted and balanced binary tree with 1 million elements, we can find any node in the tree with no more than 20 checks. The usual operations in a binary tree are add, which inserts a new node to the tree in the right place relative to its parent; remove, which deletes an element from the tree, taking along with it its entire subtree; balance, which sorts the tree so that it is optimal for searching; and find, which searches the tree for a given value in the node's data property. Note that since the algorithms required to balance and search a binary tree are quite lengthy, and since delete depends on search, note that since the algorithms required to balance and search a binary tree are quite lengthy, and since the delete operation depends on search, we will only demonstrate how to implement the add function in this section. To implement a binary tree class, we'll first create a node. This is similar to the implementation of node we've used in previous sections, but the difference here is that a node in a binary tree will have 3 attributes: the data, the left, and the right child, which will be references to subsequent nodes. The binary tree class, on the other hand, will simply hold a reference to the root node of the tree. For convenience, we're also going to keep track of the length of the tree. Adding a new node to a binary tree is actually quite easy. The only thing we need to pay attention to is to make sure that the new node is positioned in the right part of the tree. For this, we keep looking at each node down the tree until we find a leaf node where we can place the new node. As mentioned earlier, given the complexity involved in implementing some of the algorithms in a binary tree structure, we will not go through the code required to balance and search a binary tree in this section. However, let's assume that a find method has been implemented in our binary tree class. In this example, suppose that we want to keep a list of articles in memory while we do something with them at each page request. If we try to search through a list using an array, we need to search the array linearly. If there happens to be 100 elements in the array, in the worst case scenario, it will take us 100 checks before we find the article that we want, as opposed to only 6 checks if using a binary tree. What we need to do then is to create a binary tree and insert every element from the array into the tree. With the binary tree in place, we can now perform searches on it, knowing that we will find the article we're looking for very quickly. In the next video, we'll take a look at a graph, which is similar to a tree. In fact, a tree is a special type of a graph. Let's find out how so. Hello and welcome back. In the last video, we talked about binary trees and their impressive ability to organize data for super fast searching. This is video 2 of section 4, exploring graphs. Now we'll take a look at graphs and what sorts of things we can do with them. We'll begin this video by looking at what a graph is and what problems they solve. We'll take a look at commonly supported operations in a generic graph structure. Next, we'll go over a simple implementation in JavaScript. We will then look at a recommendation engine implementation using our graph data structure. A graph is a complex data structure that is made up of a collection of vertices connected by edges. As you may have noticed, a tree is a special type of a graph, and a binary tree is a very specific kind of a graph. But in general, a graph can have its vertices connected by any combinations of edges, including loops, and edges that go to and from a node in either direction or in both directions. A simple study of graph theory will show you that there are many operations that can be done in a graph class. For simplicity, we'll only look at the most fundamental operations of a graph just to get you started. Note that this particular implementation models a cyclic unidirected graph, meaning that there can be cycles or loops in the graph, and if a node A and B are connected, you can go from node A to B and back from B to A. The add node operation adds a single node to the graph. Keep in mind that at this point, the node is not really connected to anything within the graph. The add edge operation connects 2 nodes together. For simplicity, we assume that every node in the graph is an object that contains an ID attribute that uniquely identifies each node. Again, since graph theory and its related algorithms is a very complex subject worthy of its own course, we'll skip through implementation details for other things that can be done to a graph. Similar to our binary tree class, the constructor of our graph class contains a collection of nodes and a length property that mirrors the length of the array that we use to hold all the nodes. Since a graph doesn't have a root node like a tree, we don't need a specific starting point that we can make stand out. Also, the order in which the nodes appear in this nodes array is completely irrelevant, since what connects the nodes together are the edges between the nodes, and not the order in which the nodes were added to this arbitrary array. The purpose of the add node function is just to provide us with an interface that we can use to add nodes to the graph. Again, the order the nodes are added is not important. The key here is to have a way that we can store all of the nodes, as well as to increment the length property so that we always know how many nodes are in the graph. Once we have enough nodes in the graph, and technically having one node would be enough, we can start adding edges between the nodes. Since this graph class is undirected, adding an edge from node A to node B, we'll add node A as a neighbor to node B, and node B becomes a neighbor to node A. Also, since our graph is cyclic, we can create cycles in the graph by adding edges from a node to itself. In this case, we need to check that when the user creates a cycle in the graph, we make sure that we only add one link from the node to itself. In this example, we'll create a recommendations engine to help us recommend articles to the users of a website. The goal of this engine is to help us determine which articles a user hasn't read but is likely to enjoy reading. Since the focus of this example is not the actual algorithm, but rather the use of graphs, we're going to use the simplest possible algorithm to help us traverse the graph. So keep in mind that this algorithm is pretty naive, but it does illustrate the point well. The first thing we need to do is to create an empty graph and then add the nodes that represent all the data we're going to be using. Again, there's many algorithms we could use to populate the graph, but in this case, we'll just add several nodes by hand and later connect everything using the add edges method. The data in this graph will look something like this, and what it represents are all of the articles that were read by the several users of the site. In this case, article ID number 1 is being represented as being read by user ID number 15. We can see that user 15 has also read article number 2, article number 4, and article number 5. And in this node, we can see that article number 4 was read by both user 15 and 16. The reason there's an edge between the node representing article number 4 and article number 3 is because user 16 has read both of them, and thus we have a connection between the nodes. Now, the assumption of this algorithm is that since users 15 and 16 have chosen to read an article in common, they have both read article number 4, we can stipulate that since user 16 also read this article number 3, that there's a chance that recommending article number 3 to user 15 might lead to a good recommendation based on the idea that both of them chose to read the same article. So this is what our algorithm will try to accomplish using graphs. To accomplish this, we'll start out by visiting all or part of the graph, finding some or all of the nodes representing articles that the user has read and that were also read by some other user. Next, we visit some or all of the neighbor nodes from this list that we just generated, holding on to nodes that the user has not read. This will result in a list of articles not read by the user, but that were also read by other users who have read an article in common with our user. If the user has not yet read any other articles that were also read by at least one other user, we could make the assumption that this article will be a good recommendation, and we can simply return any of the articles in this list since the user hasn't read any of them. In this section, we learned how to implement a user graph and a binary tree. In the next section, we'll begin the algorithms part of the course by learning about what algorithms are and how to measure their complexity. We will also look at 2 powerful graph searching strategies. Welcome to the second half of our course. In this half, we'll focus strictly on algorithms and complexity. So far in the course, we talked about several data structures that help us write better structured code. We'll begin this section by covering the basics about algorithms. We'll talk about what algorithms are, why we should study them, and how we can measure the performance and complexity of an algorithm so that we can compare and contrast different algorithms. Next, we'll talk about 2 classes of algorithms used in pathfinding. These types of algorithms are depth-first search and breadth-first search. In this video, we'll begin by describing what an algorithm is and why we should care to study about them. We will then talk about how to calculate the complexity and performance of an algorithm so that we can compare algorithms against each other. An algorithm is a set of steps taken in order to solve a specific problem. For example, an algorithm that recommends news articles that a reader is likely to enjoy reading might include the following steps. First, we find an article that the user has not yet read. We then ask ourselves, is this article recent enough that we would want to recommend it? Is this article within the average word count that this user normally reads? Is this article about a topic that the user reads often? Does the user tend to watch embedded videos within articles whenever he or she reads the article? And if so, does this article contain such embedded videos? Based on the answers to each of these questions in this algorithm, we could calculate some sort of score, which we would then use to determine whether the article would be a good recommendation or not. Now, looking at the steps in the algorithm we just looked at, you may or may not think that this algorithm is efficient in terms of calculating the final score for the recommendation that we're after. Whether or not the recommendation is accurate is not really important for the purposes of this conversation. What we want to know is how long it would take to calculate a score for a specific article. This way, if a different algorithm comes along, we can compare them in terms of their complexity. So when trying to determine how long an article takes to run, when trying to determine how long it takes to run the algorithm, you may think that the answer depends on what kind of hardware we have running the algorithm. When describing complexity of algorithms, what we take into account is not the hardware used or the programming language that was used to implement the algorithm, or anything else that may vary for that matter. Instead, we look at how the algorithm responds to changes in the size of its input. For this, we use something called big O notation. Big O notation gives us a way to express how an algorithm performs as its input grows larger and larger. For example, let's consider an algorithm that sorts a list of numbers in either ascending or descending order. The algorithm performs the following steps. First, we take the first number in the list and compare it to the number next to it. If the number on the left is greater to the number on the right, we swap both numbers. If the number on the left is less than or equal to the number to the right, we ignore it and go on to the next step. Now we compare the next item in the list to the one next to it. We repeat the steps until you reach the end of the list. Then we start over again until no swaps are required throughout the path, at which point the list is fully sorted. While this algorithm may take very little time to sort a list of 7 numbers, it will take significantly longer to sort a list of, let's say, 1 million items. Also, there are cases when the algorithm will take less steps to sort the list. For example, if the list is already sorted or only a couple of items are out of order. Consider the case when the list is completely sorted but in reverse order. In this case, the algorithm will take the longest possible time to complete. There are 2 ways to calculate the big O value of a function. The first way is to use a formal mathematical definition of big O notation. The second way is what is most commonly used and is much easier for the rest of us to understand and requires the following slightly simpler steps. We keep the term with the highest order of growth, and in programming terms, we find the slowest operation in the function. We then remove any constants from this function. For example, looking at the sorting algorithm we described earlier, we can calculate the big O value of it for 2 types of input. The best case scenario, when the list is already sorted, and the worst case scenario, when the list is completely sorted but in reverse order. So every item in the list will need to be swapped. So suppose we have a list with 7 items in it. If the list is already sorted, then the algorithm would simply check that every number in the list is already sorted and calculate that the list is completely sorted already. A total of 7 checks will be performed. So we can say that the big O value of this algorithm in the best case would be O of n, meaning that n checks were made with the list having n items in it. In this case, it would be a big O value of n representing the list with 7 numbers. In this video, we learned how to use big O notation to calculate the limiting behavior of an algorithm. You are now able to look at an algorithm and calculate its complexity. This is especially useful when comparing similar algorithms in order to determine which one is most optimal. In the next video, we'll take a look at depth first and breadth first searching, which are two ways used to traverse a graph. Practical applications for wanting to do this includes finding a path through a maze. Hello and welcome to video 5.2. In the last video, we talked about the basics of algorithms and how to measure the complexity their complexity using big O notation. In this video, we'll talk about two types of algorithms, namely depth first and breadth first searching. The algorithms described in this video will use the advanced topic of pathfinding in order to demonstrate practical uses for graphs and stacks. If you're interested in learning more about pathfinding, this video would not be an exhaustive source, so I'd recommend that you look for a specialized book on the subject. Instead, we'll only talk enough about it so that implementing depth first and breadth first search will have a meaningful context. So in this video, we'll talk about what pathfinding is and how to solve it using depth first and breadth first search. Pathfinding or pathing relates to algorithms that find some path between 2 points. Most commonly, this means finding the shortest or otherwise most optimal path from a starting point in some map to some target point. A common way to achieve this is by representing the map as a graph data structure. This way, the starting and target points are just nodes in the graph that are somehow connected through one or more paths. This way, the solution then requires that we traverse the graph in some fashion until we reach the desired node. In other words, pathfinding algorithms generally fall into one of two broad categories of graph traversal: depth first search and breadth first search. We'll discuss both techniques and show you a simple implementation in code. The idea behind depth first search is pretty simple. We start at some node in the graph, then follow it all the way down until we reach a dead end or until we find a solution that we're looking for. When we come to a point in the graph where two or more paths are available, we choose the path to follow however we want. In most cases, what you want to do is choose the new direction in a consistent way so that the algorithm can become more predictable. Next, whenever you come to a fork in the road, you add that node to the stack. This way, when you arrive at a dead end, you simply pop off the node off the stack and continue searching the alternate path from the last fork in the road that you've stumbled upon. The implementation of this algorithm is surprisingly simple. We use the same stack class that we created earlier in the course, as well as the graph class that we created just a couple of videos ago. The first thing we want to do is to convert the map that we're traversing from whatever format that we have it in and represent the possible paths as a graph. In this case, we're representing the map as a two-dimensional array of integers where the number 1 represents walls and the number 0 represents the paths that we can walk through. Next, we'll start by adding the first node into the stack. We then continue to iterate through the graph by repeating the following steps. We'll take the first node at the top of the stack without popping it off, and we mark it as visited. This is important so that we don't keep walking around in a circle. Next, we look at every possible path that we can go to from the node we're in. In graph theory, this would be adding all of the adjacent nodes from where we are. We add all of these nodes to the stack if we haven't visited them yet. If we have visited every adjacent node from the current node, we pop off the next item from the stack and continue until the solution is found or until the entire graph has been visited, in which case we know that the solution was not found on the map. Breadth first search is different from depth first search in that it uses a queue data structure instead of a stack. Instead of backtracking to the last fork in the road, we traverse the map until we come to a node with one or more adjacent nodes from it. Each of these possible paths are added to a queue, and then we traverse each path in the queue until we come to another node with one or more adjacent paths from it. At this point, we enqueue the new adjacent path and dequeue the current path that just got us there. The algorithm is as follows. First, we enqueue the starting node and mark it as visited. Next, we visit each of its adjacent nodes and mark them as visited also. As we mark each adjacent node as visited, we enqueue them in whatever order we want, though you might want to be consistent in the order in which you add the items to the queue. Finally, you dequeue the queue and continue the process with the next node in your list. Similar to how we implemented depth-first search, we'll use our graph class from the previous lesson. We will also use the array-based queue data type that we created earlier in the course. The setup is the same as before. We'll get the map into a graph so that we can look at nodes and its adjacency list. The starting node, first we take the starting node and mark it as visited. Next, we add all of the unvisited adjacent nodes into the queue, regardless of where we are, assuming we're not done yet, meaning that we haven't found the target node we're looking for. We take the next item available in the queue and repeat the process with all of its adjacent nodes. In this section, we learned about big O value and how to calculate it. We also discussed depth-first and breadth-first search, which are great tools for solving pathfinding problems, such as navigating through a maze. In the next section, we'll talk about various sorting algorithms, from one of the slowest and most useless algorithms outside of academia to the fastest sorting algorithm known to man. This is the last section of the course. In this section, we'll cover arguably the most commonly used algorithms to solve sorting and searching problems. First, we'll go over sorting by looking at different sorting algorithms, from one of the slowest algorithms there is for sorting to the fastest ever discovered by mankind. Next, we'll go over searching algorithms by looking at two different ways to find an element within a list of elements. In this video, we'll begin by describing what is arguably the worst possible sorting algorithm there is, the bubble sort. The reason we would even mention this algorithm is purely for academic purposes, as one would never actually have a reason to implement such an ineffective algorithm. But at least mentioning this algorithm is probably a must for any course that talks about sorting. We will then talk about the two fastest algorithms we know of, merge sort and quick sort. As mentioned earlier, bubble sort is probably the worst sorting algorithm there is. The reason it's such a poor choice for a sorting algorithm is that an average sorting operation with this algorithm has a big O value of n squared. In other words, if we need to sort a list with 1,000 elements, the most expensive operation in this algorithm is repeated 1,000,000 times. The reason for this is that n passes through the list are required for a list of size n. The algorithm is as follows. We start at the beginning of the list. We compare the first two elements. If the element to the left is greater than the one on the right, we swap the values. We then take the next element and compare with the last element from the previous pair, and we repeat. At the end of each iteration, the highest value will have been moved all the way to the right of the list being sorted. Eventually, after n iterations, every item will be in the right position and the sorting is done. The only reason that bubble sort is so popular among other sorting algorithms is because of how simple it is conceptually. As a result, implementing it is trivial. The first step is to determine the length of the list being sorted. This way we know how many passes we need through the list until it's sorted. Next, we iterate from the first element to the second to last, checking the current element and the one next to it. If we ever find an element whose next neighbor is higher, we swap them. Unlike bubble sort, whose big O value is n squared, merge sort has a big O of n log n. In other words, while bubble sort takes about 1,000,000 operations to sort 1,000 items, merge sort could sort that same 100 item list in about 3,000 operations. That is 1,000 times log of 1,000, which equals 3,000. If the size of the list is now 1,000,000 items, bubble sort would take 1,000,000,000,000 operations, whereas merge sort would only take about 6,000,000. The idea of merge sort is very clever. If you have a list of a single item, then that list is already sorted. If you then have a list of 2 items, then sorting this list in the worst possible case would only require a swap in the items, and the list would then be sorted. Thus, the merge sort algorithm works in 2 steps so that this principle can be applied. The first step is to break the list in half so that we have 2 lists. We then take each list and repeat the process until both lists have become a list of a single element. Once we have n already sorted lists of 1 element each, we just need to merge all of them together in the right order. This is easy to do because as we merge more and more elements, we know that they are already sorted, so finding where the incoming elements go is very fast. Implementing merge sort is typically done using recursion and the divide and conquer approach. What we'll do here is define 2 functions, one that recursively breaks down the list in half, then we'll define a function that merges both lists into one. The first function will check if the incoming list has a length of 1, and if so, we know we've reached the end of the breaking down part of the algorithm, so we return the list. If there are 2 or more elements in the incoming list, we'll find the midpoint of the list and call ourselves twice. First with the first half of the list, and second with the second half. The merge function is a bit more complicated. We start out by creating an empty list that will hold the resulting list. We then loop through both lists being merged and push the smallest item of the 2 inputs into the output list. Once one of the lists is empty, we simply add the remaining items into the output list. Quicksort is also an n log n algorithm, just like merge sort. It's also typically implemented using recursion, although the idea behind it is fairly different from merge sort. The first step in quicksort is to choose an element in the list to be the pivot. The pivot is supposed to be picked at random, but normally the algorithm is implemented such that the pivot is always the middle of the list or the first element in the list. The idea is that after the pivot is selected, we iterate over the list from left to right, keeping track of a marker on both sides of the list. Should the current item ever be greater than the pivot, we check that item against the right marker element. If the right item is greater than or equal to the pivot, we leave it where it is and move on to the right marker. We continue to move the right marker until we find a value smaller than the pivot. Now we swap the elements of both markers and move the left marker to the right by 1 place. We repeat the steps until the markers have crossed, at which point we insert the pivot where it should be. The result from this will be 2 partially sorted lists, where the list to the left of the pivot has only values smaller than its own value, and the list to the right of the pivot has values greater than the pivot. Next, we recursively sort each sublist using the same steps. To keep things a bit simpler, in this implementation we will always choose the pivot to be the first item on the original list, as well as all sublists. Since this is a recursive function, we need to check for a terminating condition, which in this case We'll check if we're trying to sort an empty list. Next, we create two empty lists that we'll use to populate values that are lesser and greater than the pivot. We then traverse the list, adding values lesser than the pivot to the list on the left, and greater or equal values to the right list. When we're done, we concatenate both lists with the pivot in between the two. The algorithm is repeated on each subsequent sublist until the resulting sublist is empty, at which point we start popping up the recursion stack. This video covered three of the most commonly used sorting algorithms. Although bubble sort is only used in academia, merge sort and quick sort are the sorting algorithms of choice in most other software engineering use cases. In the next video, we will look at linear and binary search. As we'll see shortly, searching becomes significantly faster when the search space is sorted prior to searching, in which case we can choose the fastest searching algorithm known to man, binary search. In the last video, we talked about two n-log-n sorting algorithms as well as the classic bubble sorts. In this video, we'll talk about searching using an unsorted list and a much more performant search over a pre-sorted list. Let's take a look at two ways to search for data in some collection. As you'll see, the type of collection we use to search will influence the performance of the search algorithm a great deal. One other important detail is whether we're searching a sorted list or an unsorted collection. The first search algorithm we'll learn is the ordinary linear search. Next, we'll look at possibly the fastest way to search a collection that there is. And for this, we're going to use the binary search algorithm. As the name implies, a linear search is a type of search where we look for the desired item by iterating through a collection one item at a time. As long as the collection allows us to visit each element in order, we can linearly search over it. Whether the collection is sorted or not makes no difference when performing a linear search. The speed that it takes to find an item, provided that the item is in the list, will grow proportionally with the size of the list, making this algorithm a big O value of n. To implement linear search in JavaScript, all we really need is a way to iterate over the collection. In this case, we'll use an array so we can take advantage of the many iterating methods in the array's prototype. Since we want to stop the search as soon as we found the answer, using for each, map, filter, or reduce is not a good idea since there's no way to break out of those loops. What we could do is use a while loop or a for loop. For no particular reason, let's go ahead and use the array's sum method, which breaks the search as soon as we return a true value from the predicate callback. For those not sure what a callback function is, it's just an ordinary function that is passed to some other function as the argument. The receiving function can then invoke the callback function at any point in time that it needs to. Note that using a predicate function allows us to use a custom matching criteria, but this is optional. Depending on the data set and your use case, we could very well make some more assumptions about the data structure we're using and inline the data matching part of the algorithm. In this example, we're creating a list with 10 items in it. The values of the items will be the integers 0 through 9. We will then do a linear search for this over this list, looking for the first item in the collection that has a value greater than 5, and also an item that is even. Contrary to what you may think, performing binary search does not require a binary tree. The concept of a binary search is simple. The only requirement is that the collection be sorted prior to searching. First, we find the center of the list. If the item we're looking for is at that location, then we're done searching. If the item we're looking for is not at the center of the list, and the value at the center is smaller than the value that we're looking for, then we continue our search, but reducing the search space in half by only looking at the second half of the list. Again, we find the midpoint of this new sublist. We check if that element is what we're looking for. if we still haven't found the answer, we check if the item that we're looking for is to the right or to the left of the center and create a new sublist accordingly. In summary, we keep breaking down our search space in half at each check. This makes binary search an algorithm of a big O value of log n. In other words, if the list we're searching over has 1 million items, it will take us no more than 20 checks until we find the item, or until we conclude that the item we're looking for is not in the list. Similar to our linear search, the structure we use to perform binary search does not matter, as long as we can iterate over the list by accessing whatever item that we want. In this case, let's go ahead and use an array. We find the midpoint by dividing the length of the array by 2. If the element at that location is what we're looking for, we're done searching. Otherwise, we slice the array and continue the search. If the smaller array has a single element in it, we need to first make sure that that item is not what we're looking for. In this particular example, we first create a list with 1 million elements. We generate a random value between 0 and 10,000 and perform binary search over our data, which will take us no more than 20 checks until we find if the item is in the list. In this section, we learn about searching and sorting lists. We discussed the bubble sort algorithm only to be polite to it. We also learned about merge sort and quick sort, as well as the benefits of sorting a list prior to searching it. And this concludes our course in data structures and algorithms. Now you can use JavaScript's native collections, such as arrays, maps, sets, more fully by taking advantage of built-in methods such as map, reduce, filter, sum, all, and others. You are also able to build your own data structures whenever you need more specialized constructs for your apps, such as stacks, queues, graphs, trees, to name a few. Finally, you now know how to analyze algorithms in order to calculate their runtime complexity. With this powerful skill, you can now optimize your own algorithms or decide between alternatives when choosing an algorithm strategy for your apps, your games, or whatever else you choose to develop. If you'd like to reach out to me to clarify any questions or to give me any feedback, feel free to do so at my personal website at rodrigo-silveira.com. There you will find links to social network sites that I use, such as Twitter, Facebook, Google+, GitHub, and YouTube. I hope you've enjoyed this course, and I thank you for your support and your interest in becoming a better software developer.